they are constrained. So there are some relation between different dynamical variables. And that means the system is constrained. And in mechanics, of course, you met sometimes the system which are constrained. For example, if you have the system, some material point which rotates on the circle. There is some rigid, like this, for example. Okay, so there is a constraint. My system is fixed here, so it goes only over the circle. Yeah, it cannot go away. So there is a constraint. The same is here. And in fact, I said that second Noether theorem tells us that not all the components of A mu are independent. They are not all of them are observable. And in particular, the component, if you look more carefully at the Dirac-Max or Dirac-Lagrangian, you will see that the variables A0 is not a canonical variable. If you will try to compute the canonical momenta conjugated to A0, and canonical momenta, I remind you, is dl differentiated with respect to A0 dagger. Okay? It's identically zero. There is no canonical momenta conjugated to A0. And A0 enters in the following way. A0 multiplied by dEEI minus dIEI minus G0. And J is a current, that means psi, gamma 0 psi. Okay? What does it mean? Of course, that means that A0 in fact is Lagrange multiplier. If you vary with respect to A0, you will have a constraint. And what is a constraint? Everybody of you, I guess, knows it. It's just Gauss law. Gauss law means that the divergence of electric field, dIEI, is equal to the charge. If I integrate G0 over space, it's charge. So this is just Gauss law.
Density of charge.
Density. Okay, now if I integrate over x, then it's charge. If I'm the integral, then of course density of charge, yes. And one can also see that the divergence dIAI is changed by the gauge transformation in arbitrary way, by this gauge transformation. And so if I will count the degrees of freedom, I will get just the right answer. So let us first of all think, what are the number of degrees of freedom of electromagnetic field? You know that electromagnetic field is transversally polarized. What does it mean? That means that the light is always polarized in the plane which is perpendicular to the direction of its propagation. Okay? So that means there are 2 degrees of freedom, only 2. 2 vectors. In the plane you can introduce 2 vectors and then you can expand any vector in this basis. And this is exactly the number of variables which remains when I use the constraint equation and impose some gauge equation. Gauge equation means that I use alpha in such a way as impose one condition on the field A mu. And so, originally I had 4 components, A mu. A mu had a 4 components, okay? Now, as you see, A0 is not a dynamical variable. A0 is just a Lagrange multiplier. And I can also, dAIA may be changed in arbitrary way by this transformation. So 2 components of A0 I can, in this way, eliminate. And I am left only with 2 components, 2 degrees of freedom, precisely like for electromagnetic field which we observe. So everything is in accordance. Now, before the last, let me firstly show you one more slide. I mainly discussed up to now still the free field. And now, at the beginning of my lecture, I mentioned that quantum field theory describes the processes of creation and annihilation. And here I showed you some examples, and they are of course written in terms of Feynman diagrams. Again, I think majority of you knows what it means, but anyway, up to now you can just consider it as a pictures. It doesn't matter, it's not so important what is inside. For example, the lowest order Feynman diagram. If you have electron may emit, first of all, they annihilate and produce virtual photon. This is photon line, okay? So they annihilate. And here there's also electron. Oh, here they are not, sorry, I'm not right. Here there is a real scattering. So electron emits photon, and this photon is absorbed by another electron. So this is a process of scattering by exchange of photon. Yeah? So this is one electron, this is the second electron, and this is exchanged by photon. This is another diagram which goes by annihilation. So here, two electron and positron annihilate here. There is a virtual photon, and here also the creation of virtual pair. So there are two processes which are described by Maxwell-Dirac-Lagrange. But if you go further in perturbation theory, if you try to consider more complicated process, you will discover the diagrams which are written here. One electron can emit virtual photon, this one, and then the same electron would absorb this photon. Okay? The same can be done by photon. The photon creates virtual pair of electron and positron, and then they annihilate. Again, there is a propagation of a free photon. More complicated process, there is electron which emits virtual photon. Then again there is a absorption process, and there is emission of photon. So this triangle diagram. Electron, electron, and photon, etc. There are infinitely many diagrams. But, okay, up to now that was just pictures. But there are rules in quantum field theory, which I will not discuss, but probably in the course of a normalization, which will be discussed by Professor Shirkov and Budnev, you will say, know something about it. If you calculate the corresponding matrix elements, they are meaningless, they are divergent. So you can write, of course, integrals corresponding to these diagrams, but you cannot calculate them. They are divergent. And that was some obstacle for quantum field theory. But this obstacle was overcame mainly in 50s, following the ideas firstly put forward by Hans Bethe, the idea of a normalization. The point is that why, in general, all these infinities appear. And the reason for appearance of these infinities is the following. Okay, we know, of course, about interaction of electron and Hamilton and electron and photons at some energies, but not too high. Even in our best experiments, if we use LHC or any experiment, the energy is still limited. There are energies like Planck scale, which definitely are not accessible in our experimental in our experiments. And we know nothing about the behavior of system at these very high energies. And if you think, then you may say, okay, probably it's hopeless to try to describe our low, so to say, low energy. Of course, low energy in quotation marks, because for everyday life it's still very high energies, but nevertheless, let us call it low energy physics if we know nothing about high energies. Fortunately, the God is not cruel. You know, he's just very imaginative, but not cruel. So, for the most important theories, it happens that we don't really need the exact knowledge of details of interaction at very high energies. And indeed, if we consider, for example, quantum electrodynamics, then all these infinities may be removed by the process of renormalization. What is the idea of renormalization? Suppose we consider the theory only for not too high energies. So we cut all momenta by some parameter lambda. Okay? Of course, it will destroy Lorentz invariance, but one can do it in a more elegant way without destroying Lorentz invariance. For the moment, I don't care about it. So let us just cut all the momenta by some parameter lambda. Then we don't know, we don't care about the behavior of our system for very high energies. All the energies are limited by this lambda. Okay? But of course, what to do then? Then we have explicit dependence of all our processes on lambda. And this dependence is such that for large lambda, the contribution of these energies is very large, because we know that the integral diverges with the limit when lambda goes to infinity. Okay? It happens that all the dependence on lambda may be eliminated if we allow the parameters of our classical Lagrangian, of our original Lagrangian, also depend on lambda in some special way. We should only assume that the charge, electric charge, depends on lambda. The mass of electron depends on lambda, and also normalization constant of wave function also depends on lambda. And then, if you consider, for example, this diagram, I said you that it's divergent when lambda goes to infinity, this diagram. But if I allow the dependence of, say, normalization constant for the wave function also on lambda, then I should consider with this together